Okay, so in this configuration, it's of all the different ring systems, this is the one that has the lowest overall energy because it can avoid all of the unfavorable interactions of angle strain in the molecule as well as any kind of eclipse interactions. So here we have essentially no angle strain. The angles are close to 109.5 all the way around that carbon ring system. And there's essentially no torsional strain. All of the CH bonds around that ring are in a staggered conformation, which we know is the most energetically favorable. It's the lowest in energy. Right? So no angle strain. And also, essentially, no torsional strain. So here our angles are close to 109.5. And here, all CH bonds are staggered. Right? And we're going to talk about drawing this in a minute, but what I want to do is I want to show you. This is a chair cyclohexane. So we call this a chair because if you look at this, it's maybe not as easy to see on this model, but if you look at this, right, this is sort of like a Hawthorne model drawing where we demonstrate in a ring system the side that's out of the plane of the board by making it more bold. So this is like a wedge bond, and then we have a bold bond, and then we have another wedge bond. So this is in the front. But that to me kind of looks like an Adirondack chair. Right? And that's why it's called the chair configuration, is because it kind of looks like a chair. You can, if you look at it hard and you squint a little bit, maybe you can see this is an Adirondack chair. Maybe it'll help if we rotate it a little bit, but you see we have some legs down here, and I can kind of, if I try to stand this up, I already tried to stand it up on the table. The table's not quite big enough, but you can imagine that here, here, and here, these lowest hydrogen atoms, that these would kind of stand like this, and you have what would look like a chair, right? That's kind of why it's called that. But if we look down, a couple of the carbon-carbon bonds here. So if we look down this bond and this bond, we end up getting a structure that looks like this with two Newman projections and then tethering those two together with those linkers, right? So it would effectively look like this. And so if you look down, it's hard to look down both at once, but if we look down one, you can see that the hydrogens here are staggered, right? So those hydrogens are staggered on that bond. But not only are they staggered on that bond, every single one of the bonds as we go through, we will also have a staggered configuration. Right? Every single one is staggered. Right? So this is why a cyclohexane in a chair configuration is most stable, because 109.5 degree angles throughout, and all of my carbon hydrogens are in a staggered configuration, right? All the way around. So that's basically the chair configuration. And then there's another configuration that we can access, which is higher in energy. But if I take, and of course we talked about all of these carbon-carbon bonds being like strings of spaghetti, right? So they can flip around and they can go in any direction. The same is true for a cyclohexane. So if I rotate my string of spaghetti here in the string system and I put it in a configuration like this, I've got a new structure as far as the configuration goes. And now this one, if I turn it sideways here, right? I think it might just fit here and stand. This is the boat configuration. And so, another configuration that you guys need to know. And this is the boat configuration. And who wants to guess why it got its name boat, right? Kind of looks like a boat, right? Every time I look at this, I see like a Viking giant rowing boat with like stuff on the side. But anyway, it looks like a boat. Right? Now this one isn't as stable as the chair. In fact, it's a lot less stable than the chair. Because if we look at this one, while the angles are all pretty close to 109.5, if I look down, the bonds on the side of my boat, right? So this is maybe the bow, and this is the stern of the boat, and then I have the left side and the right side, the port side. What's the other one called? I forget. Anyway, starboard. Yeah. So if I look down that, you can see that as I'm on the right or the left-hand side of my boat, right? If I look on that side, or if I look on that side, these hydrogens are eclipsed, right? So we know that there's an energy penalty for being in this configuration because of that eclipse interaction, right? And by the way, what does that energy cost again? How many kilojoules per mole is it for each of these? Richard? 4, right? So it costs us 4 for every single one of these, right? And so these add up. So while there's no angle strain, we have 4 pairs of eclipsing carbon-hydrogen bonds, on each of these carbons on the side of my boat, the left and right-hand sides. These and these are eclipsed. So I have 4 pairs of eclipsing carbon-hydrogen bonds. And then there's another interaction, and I'm actually going to pull out a different color since I have this awesome model set that I can use. So that you can really see this in space. Uh-oh. Oh, I just pulled that right off. But if I put on a green atom in these 2 positions, you can see that these are actually pointing a little bit towards one another. In my boat, with 109.5 degree angles, these 2 are called the flagpole interactions, as you can see up there. And these are even closer towards one another than the eclipsing carbon hydrogens on the side, right? So there's a penalty for that as well. So we have a number of different interactions in the boat which lead this to be a lot less stable than the chair configuration, right? So while one, we don't really have any angle strain, we have about 109.5 degree angles throughout our carbon chain in this ring. We do have torsional strain. And that is 4 pairs of CHs that are eclipsed. Right? And then we also have that extra flagpole steric interaction. Right? So for my molecule, if it has a choice, right, and there's enough energy to interconvert these forms, which one's going to be favored, the chair or the boat? Which one am I going to have more of? The chair, right? It's lower in energy. So if these things can interconvert, and we know, because this is basically just a floppy string of spaghetti, right, that I can just do that. And I can get to a chair again. Right? So my molecule typically has a choice, and it can interconvert, and it's going to make the more stable conformation, which is usually going to be the chair. Almost always going to be the chair. Right? So that's a little bit about the boat, and you can see here we can use a Newman projection to draw it like this, and here's another one of our Hawthorne kind of drawings, which really shows this flagpole interaction. Right? Any questions on that? So I want to show you another conformation with this now. I'm going to flip this back up again. Again, now we're in the boat. Doesn't really want to be in this boat. It's pretty high in energy compared to the chair, but it is an accessible conformation. But if I take this and I twist it a little bit, right? if I twist a little bit, where I used to have these eclipsing interactions, I can start to avoid that 100% eclipsed, right? They're not directly eclipsed anymore. They're not really staggered, but they're also not fully eclipsed. This is another one. So if I twist this way, then the other one twists a little bit the other way, and so on both sides, I avoid a little bit that direct eclipsed interaction. So that's another one of the named conformations for a cyclohexane, and that's called a twist boat. Okay? But it's actually pretty similar to the boat, so we're not going to talk about that one in too much detail. Basically, we avoid a little bit of the torsional strain and a little bit of the flagpole interaction because these are all canted a little bit. Right? And you can see that the energy difference between the boat and the twist boat, where the boat is 30 kilojoules per mole more high in energy compared to the chair, the twist boat is only 23 kilojoules per mole higher in energy than the chair. So the twist boat, 7 kilojoules per mole lower in energy than the boat. And that reflects the avoidance to an extent of those eclipsed and flagpole interactions. Right? Make sense? Everybody get it? Anybody not get this? Raise your hand if you don't get it, and I can try to explain it a bit differently. Everybody got it? All right, great. Okay, so I want to also mention this other conformation that's way up there in energy, 45 kilojoules per mole, higher in energy than the chair. So if I go back to my chair, I'm going to flop my string spaghetti like this. I'm back into the chair. Right? Now, in order to go from this chair, imagine I'm down here in this low energy spot. In order to go from this chair into the boat configuration, as I start to turn my floppy string of spaghetti, right, I get to a spot right there. And my models don't even want to hold this spot. Right? Because as I get here, I start to have a little bit of angle strain. But importantly, also, if you look down that bond there, I also have eclipsing interactions between these carbon hydrogens. It's green, but this is also, it's a hydrogen, same as this one right now. We're just highlighting it as green to show the end of our boat, right? That's eclipsed, right? So now I have 1, 2, 3 carbon systems in a row with all of the carbon hydrogens all being eclipsed. And we know that that's going to raise the energy of our molecule, right? But our angles are also not quite favorable at 109.5. Right? So that half chair, because this side is sort of in a chair configuration, but this side is sort of completely flat. Right? This half chair is a conformation that we end up going through to get to these other, the twist boat and the boat, to get over to here. Right? It's just what we have to do to get there from here. And so we have to go up in energy to get to the boat, and to go from the boat back to the chair, we have to go up in energy and back down again. These can all kind of interconvert. We don't have to go directly from the boat through the twist boat to the half chair. We can go from here directly to the boat, right? Without twisting. But to go from the chair to the boat, we end up, at some point, we end up having to pass through the situation where these guys are all in the same plane. So that's a little bit about the different energy levels of these. But the important take-home messages here, the ones that you'll often see on exams, would be the chair configuration, which is the most stable. It's the one that I'm showing you right here. Right? And then you'll often see the boat as number 2. But the twist boat and the half chair you may also see. So knowing these is really important. All right. Now, when we try to draw this in 2 dimensions, there's a little bit of art and skill involved. I'm not that artistic. I draw these things very quickly. But I'm going to do my best to draw this for you so you guys can see exactly how this works. Okay, there's like at least 3 different ways to draw them. I'm going to show you a couple, and hopefully you guys will find a way that you like it. So one way is to draw 2 parallel lines. right? Sort of like this. Cant it over a little bit. And then, when you draw the rest of the molecule, you're just drawing the wedge up on one side. So it goes up, and then back down again. And then on the other side, you do the same thing. Trying to get the angles just right. I don't think I got it quite right, but it's pretty close. And when you're done drawing the chair, the important thing I want to highlight is we have a pair of parallel lines here in blue. We have a pair of parallel lines in purple. And we have a pair of parallel lines in this pink or red color. Right? So when you draw a chair, if you've done a good job drawing it, you should have 3 pairs of parallel lines. Okay? Now, you don't have to draw the parallel lines and then the parallel lines and then the parallel lines. You know, when I drew this, I drew the first 2 and then I drew the wedge and the wedge. Now, if I'm drawing this quickly, what I usually do is I just start from one side and go to the other. So I draw a wedge like this, and then I draw my 2 parallel lines, and then I draw a wedge on the other side. Right? That's a third way to do it. So we have draw the first 2 parallel lines, and then draw the wedge and the wedge, or you can just start with a wedge, and then draw it across from sort of left to right. Now in the book, what it describes is basically drawing a V, right? Let me move this over a little bit. I'm going to actually erase the boat configuration here. We're running out of space there. Right? When in the book it describes a way of drawing it where you draw sort of a V here. And then you draw a line down from this direction here, not all the way over so that you pass a vertical line here, but you draw it down to about there, and then you come back up parallel to this line, and you stop about like that, and then you draw a line down, which is going to be parallel to this line, and then you draw your line back up, which is parallel to this line. So you end up with a chair that way also. So this is something that takes a little bit of practice. Any of these different ways of drawing it will work just fine. But in the end, what you really want to have is these parallel lines. You want to have 3 pairs of parallel lines, and then you'll have a really well-drawn chair. Okay, any questions on that? Everybody have it? Yeah? It's pretty straightforward. So, after we have drawn our chair, right, then what's going to come next, and I'm going to draw it so that I have the colored lines over here again. But if I'm drawing my 3 pairs of parallel lines, right, I'm going to stick with the same color scheme. Right? I end up with my 3 pairs of parallel lines, and then to draw the hydrogen atoms on these, I have 2 kinds of directions off of my chair. And those 2 directions are referred to as axial or equatorial. So on each of these carbon atoms, we're going to end up with 1 hydrogen which is axial and 1 hydrogen which is equatorial. Now the axial ones, they're really easy to draw because they're just sort of straight up and down. So they're all the lines for those are going to be parallel and they're straight up and down, essentially. So I'm going to have 3 that are straight up. These angles that point up, I'm going to have the axial hydrogen pointing up. And then the three angles that are down from my carbon system, I'm going to have the carbon-hydrogen bonds pointing straight down. So those are all the axial ones. There's one axial carbon-hydrogen on each of the carbons of the cyclohexane. Okay. And then after that, we end up, for the equatorial, we're making lines that are, again, parallel to some of these lines that we've drawn. So on this carbon, and it's always sort of like one bond over from that particular carbon. So this carbon has a bond attached to it, and then there's like one bond over on both sides. Well, the hydrogen, the equatorial hydrogen, is actually parallel. The angle that you draw is parallel to these other two. So there's one. And then on this one over here, go over 1, 2 bonds. It's going to be parallel to that. And then if I look one more carbon over, if I say look at this carbon, right? And not the bonds that this carbon is attached to, but one past that, so 1, 2 bonds away. Now this one is going to, the carbon-hydrogen bond is parallel to that pink one. Right? Same thing for this one. 1, 2 bonds away, it's going to be parallel to the pink one. Right? I have 2 carbons left, and guess what they're going to be parallel with? Purple one, right? So I'm attached to this carbon, it should be parallel to 1, 2 bonds away, so it should be parallel to that purple bond. And then on this one, it's parallel to the purple bond right there. Right? So we have the axials are going to be vertical and all parallel. And the equatorials are going to be parallel to the carbon-carbon bonds that are 2 bonds away. Make sense? So when you're drawing these, if you draw it like this, if you spend 15 minutes drawing these out today, you'll have this locked in your mind and you'll get it right always going forward. I strongly suggest that you do that, because this is something that you're going to see repeatedly in Organic 1, in Organic 2, very likely to be on the exam coming up, very likely to be on the ACS final. Okay? So drawing these is important, and not only drawing them, but also understanding the energetics that are involved. So if I go back to this system and let's take this one. If I go back to my cyclohexane, right? If I have one substituent on this, right? Actually, let me do something first before you do this. I just want to catch us up in the slides where we are. This basically just talks through several of the things we did. So this is how to draw the chair properly, right? And also the axial positions, and these are the equatorial positions, and showing that you draw them in parallel to some of the other bonds. Right? And then a drawing that shows the different axial and equatorial bonds. Right. So if I, however, have a single substituent on my system, and let's say that it's not just a green ball. It's not a highlighted hydrogen atom. Let's say it's a methyl group. Right? Now this methyl group that's attached to my cyclohexane chair, right now, what position is this in? Is this an axial or an equatorial position? Ah. Can you tell? So if I have my chair, right, and it's like this, right, so this is the sort of like the foot of my chair, this is the head of the chair, these are my sides of the chair, right, this is pointing up, right? Everybody see that? It's pointing up here. And then does this go straight up, or is this parallel to the bonds of my ring system? Straight up. Straight up, right? So does that make it equatorial or axial? Axial, right. So this is in the axial position. And now, which do you think is going to be more favored? Like this, where is this starting to have an interaction with these hydrogens over here? It's almost like the flagpole interaction, right? Sticking out right over towards them, right? But if I do a ring flip, and what a ring flip is, if I turn both the foot of my chair and the head of my chair, if I flip those to the opposite side, right, I can end up with another chair. So watch carefully. It's almost like magic. I'm going to take my string of spaghetti on this side, and I'm going to flip it up, right? Oh, that's really bad, right? Now I'm in a boat, and holy cow, these guys are like touching each other. So this would be really high in energy, right? But I'm going to flip this other side. May actually happen in the other order if you're going to do a ring flip in real life. It's probably a lower energy path, right? So it would be more likely to go through the other path, where I flip this one first and then that one. But in any case, I flip both of them, and I flip the entire system. So now what used to be the foot of my chair is now the head, and what was the head is now the foot of my chair. But now, what position is my methyl group in? Is it axial or is it equatorial? It's equatorial, right? It's no longer pointing straight up away from the ring system. Now it's parallel to these other bonds that are sort of two bonds over, right? It's sort of pointing straight out. And if I look at this a little bit more carefully, right, I have an alkyl group on this side, and what kind of position is that in? This methyl versus this alkyl group, if I'm only focusing in on this Newman projection, what kind of structure is that? Is it gauche? Is it anti? Is it eclipsed? Is it staggered? Not staggered, right? I'll give you a choice of two. Is it eclipsed or is it anti? Anti, right? They're pointing on opposite sides of my Newman projection. If I had this be the front carbon, this the back, this would be back and down, this would be front and up, right? So that's the most favorable energy conformation if we just had two methyl groups about a carbon-carbon bond, right? And that turns out to be the most stable conformation also, right? We're avoiding all those negative interactions that cost us energy in the other position where this is axial. I'll draw that, I'll not draw it, but I'll actually flip it again. So if I flip this side down by twisting those guys, and I twist these guys the other direction, right? I end up with a chair with this axial, right? And I have that interaction that I don't want to have. And then if I look down this bond, right, I can see that this is a gauche interaction between my methyl group and the rest of the ring system. Right? These are adjacent to one another now. Not eclipsed, but they're adjacent to one another in sort of like a staggered conformation where my two big groups are next to each other. Right? Makes sense? Everybody can see it? Yeah? So if I have a methyl group on my ring system, which do I want to have? If I can interconvert these, which is going to be present at equilibrium? The one where it's equatorial or the one where it's axial?
Equatorial.
Equatorial, right. It's going to be lower in energy. So if we think about this, and this just talks through, the next slide or two just sort of talks through what we talked about now. But these guys can flip, and it will go from axial to equatorial. And we just rotate about these bonds to be able to get there. This is the string of spaghetti, right? So we can just rotate these. If you guys have models, I would suggest that you do this. Actually build a cyclohexane and go through the ring flip. It's actually quite enlightening to do it with your own hands. You're also welcome to stop by my office hours after class today. I'll have this large model and you can flip it, or flip it right after class. Right? Now, if we have enough energy in our system to be able to flip this, which at room temperature, most of the time we have plenty of energy to do these ring flips, you guys correctly pointed out that the equatorial is actually going to dominate. So we're going to end up with about a 95-to-5 ratio of the conformation where that methyl group is equatorial versus about 5% where it's axial. Okay? And that just reflects the difference in energy between the two. Right? We talked about some of these, but we have that in the axial position, as you can see here. These guys are sort of pointing at each other, and so if you have this group here and it's just drawn with this big ball here reflecting the larger methyl group, compared to the carbon hydrogens, these bump into each other a little bit. This is called a 1,3 diaxial interaction or 1,3 diaxial strain. Okay. So when that methyl group is axial, you pay a price for that. All right. So, and this goes through the interactions that we were just looking at with the model. So we have a gauche interaction. If you just imagine this being an ethane with a methyl attached on each end, you can see that these would be gauche. And if you look at this Fisher, the Newman projection of the cyclohexane, when we're looking down the two bonds on the side, you can see that this is sort of a gauche interaction between the methyl group and the ring as it wraps around. Right? That's what we were just pointing out. And in the equatorial position, when it's equatorial, this is more like an anti-configuration. So it's more stable that way. Right? All right. So as we go through, you can imagine, it doesn't have to just be a methyl group. If you have another group here, if you had an ethyl group, right? If you had a CH3 here, then the penalty in having it be axial would be a little bit larger, right? But maybe you could have the string of spaghetti rotate over here and the methyl group sticks out here, so it's not that big of a difference in energy, right? But you can imagine if I had a T-butyl group here, so not only did I have this carbon, but I had a carbon, 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 this is really big, and now this is definitely trying to occupy the same space. Because we'd have another carbon-hydrogen bond here, and another one over here, and it would be really sterically encumbered. These would be trying to occupy the same space. And we call that a steric interaction, right? So it turns out that a lot of these interactions have been measured. So how much does it cost in energy to have the axial versus the equatorial for a lot of different substituents? And so here's a list of them that I would say would be good to know. So much like the carbon-hydrogen eclipse interaction, right? You can start to look through these. And this just refers to the difference in energy between the axial configuration of that substituent versus doing the ring flip and getting to the equatorial position for that substituent. So the equatorial is always going to be more favorable because it avoids those interactions, right? And you can see by how much here. So the chlorine, right? It's not that big. It's just a large single atom, right? So the difference is only 2 kilojoules per mole. For hydroxyl, you know, it's got the oxygen, plus it also has another atom attached. It's 4.2. For the methyl, that interaction is 7.6. Right? So you can imagine this interaction is sort of like gauche interaction. So how much is that gauche interaction? What did we talk about? How much is that worth? It's worth like 3.8. Is that what it was? The gauche interaction for between two methyl groups, right? But then, so that would just be like doing this.